One line can carry only one binary bit at a time. So if you want to increase the speed, it needs the binary information at much higher rate. But this one can deliver only 256 bit at a time. Memory can have terabytes of information. It can run in gigahertz or hundreds of gigahertz speed. But this bus size is restricting the speed. So that is called, this bus size is called memory wall, and that is the number one limitation of von Neumann architecture. Yes.
Is it the memory lane they talk about?
Yes.
The
Memory
same thing?
bus size, memory lane, memory byte size, there are different terminology they use.
So I have a question. So the Intel Core i7 13 Gen has, let's say, 16, but the server CPU which have EPYC, which has more bus line, so you can connect more RAMs and more storage with it because it has a bigger bus line. That's the reason?
That's the reason. So it's like an interstate highway. 4 lane, 8 lane, 12 lane, 16 lane. The more lane you basically add, you can connect more service roads without any congestion.
For the electrons.
Yeah. Because one line can carry one binary bit at a time. That is the limitation of electronic communication. What is the advantage of RF communication and optical communication? Through modulation, amplitude modulation, different types of modulation you can apply, right?
Yeah.
Phase modulation, right? All this modulation, one RF channel, one wireless channel can carry like hundreds and thousands of signal at a time using multiplexing. Optical fiber that is going through under the water from New York to London, probably 1 or 2 big optical fiber carrying like millions of channels, communication channels, because multiplexing. But electronic wired communication has a limitation. It can carry only one electronic signal at a time. And all the digital electronic computers are limited by this lane size or bus size, memory lane or memory bus. So now, what is the future solution? Future solution is, can we merge this memory and CPU into one unit, eliminate this bus. That is, same set of devices or circuit nodes or circuits will work as memory if needed and CPU if needed. Any example you can think of in our day-to-day life, cells or devices that work both as a memory and signal processing.
I saw one of the videos, some researchers are doing research, they're trying to make memory and the storage at the same time by changing the phase of the material.
You are talking about
the
memory and storage is the same thing. You are talking about memory and the signal processing.
Okay.
The CPU, computation and storage. This one is storage, this one is computation.
Yeah, the memory.
They are separated by this bus. This is restricted. Currently, we can add maximum 256 lanes in this highway. Yes.
I know, I think it was actually an Intel project that I saw, but it's based on like this whole drive towards neuromorphic computing, where they do break things up into these cells.
You have the term neuromorphic computing, but I'm looking for a very common day layman example. Human brain.
Yeah.
Neuromorphic computing is the thematic implementation of a computing system following human brain. So every cell in our human brain is designated for different function, different emotion. But every cell, it is processing the signal, it is also storing the information. So human brain lab computing, the formal technical word for it is neuromorphic computing. It can, so the neurons in human brain can store information, can also process the information to make decisions, right? So, the future, one of the direction is merging them together. It's called And then there are different versions of memory CPU merger. Another technology called in-memory calculation, in-memory processing. That is, you embed those CPU units inside the memory. So you eliminate those bus requirements. Or neuromorphic computing. You design some cell that can be used as a memory sometime, that can be used as a computational device sometime. Go ahead.
I have two questions. So
Yes.
first question is, sorry for my mistake. I think I saw that the RAM and the storage,
Yeah.
they're trying to combine that. I don't know how they're doing it. So
Are you talking about the? So when we say storage in any microprocessor system, there are two types of storage. One is called cache memory. One is your secondary memory, hard disk or flash drive, which is outside your system or on the motherboard. And cache can be two types: on-chip cache, off-chip
Off-chip
cache.
cache.
Now, off-chip cache and RAM, that can be merged together. Same set of RAM, a portion of it you can dedicate for cache application, a portion of it you can dedicate for regular RAM application. Probably you saw some of those concepts.
some of the
Yes.
concept.
Typically, in any types of digital system, you have on-chip cache, you have off-chip cache, you have off-chip RAM, and then you have off-the-system flash drive or hard drive or optical drive. So in summary, go ahead.
I remember, like, probably more than 5 or 10 years ago, there was a bunch of news about using basically quantum spin to differentiate between electrons, so you could feasibly, with one bus line, send 2 bits at the same time.
Yeah.
Was there any progress?
Welcome to quantum computing. So there are several leaders in quantum computing. All the big companies like NVIDIA, IBM, Intel, AMD, everyone is working on quantum computing. But among the startups, newcomers, one of the, don't buy the stock, I'm giving you the symbol, then you blame me. So among the newcomers, IonQ, this is one of the leading startup in the quantum space. So the idea is, and then another one is Qubit, another one is RGIT or something, I forgot. The reason it actually caught my attention, because just last 2 days, this stock increased by 100%.
Whoa.
So, from $12 to $25, $24. But please don't tell anyone that I am advising stock in the price. No, because the name, I read all the article on quantum computing. And in those articles, these names actually mention that among the new players, along with the traditional players. So what is a quantum computer? Electron spin, it's like a quantum energy, that is a very deep physics. So electron spin can have different phase. So as electron is traveling through a medium, whether it's a wire or any medium, depending on the phase and magnitude of its spin, each phase and each spin can be treated as one unique information. So the quantum computing technologies, what they are trying to do, like binary information, I raise the voltage high, I consider it 1. I lower the voltage, I consider it as 0, right? Can I create and control, it has to have, can I control 5 or 6 or 10 or 12 different spins of an electron flowing through a wire, and each of that state can be determined as one unique information. So saying one electron, single electron, can now give you 12 different sets of information. In case of binary, it's only 1, right? You can only get either 1 or 0, right? High or low. So quantum, similarly in magnetic memory, they are trying to utilize magnetic states as the information, right? In digital electronics, post-binary digital memory, what they are trying to do, there are many technologies for memory. So we know that ground voltage is 0, VDD voltage is 1. This is simple electronic memory, right? Now, post-binary, well, they are seeing that why you have to only define 0 and VDD. Can I have 0.25 VDD at another state? Can I have 0.5 VDD another state? Can I have 0.75 VDD another state? So I can have 1, 2, 3, 4, 5 binary variables between 0 and VDD, or 2 or 3. That is called multi-value digital logic or digital memory. And there are people are working on it. Instead of just only taking one state from 0, one state from VDD, can I take more than one in between 0 and VDD? That becomes called post-binary digital memory technology. I have predetermined steps, but multiple steps between 0 and VDD. There is one. The other one we just talked about, quantum. And the other one we mentioned, magnetic memory. The magnetic flux, magnetic direction, which way the flux is going, the magnitude and angle of the magnetic flux will determine memory state. That is called RAM, magnetic memory. So there are different memory technologies currently under investigation, and the most important, quantum memory, quantum information processing. That concept has been there for last 50, 60 years. But only recently, last 10 years, people have started taking it seriously, and every university is now trying to hire faculty member in quantum computing. As of this week, we, the electrical and physics faculty member, we are meeting to start our first course on quantum computing next year.
We're actually
So
also
in ECE?
It will be offered both to ECE and physics students.
We're also opening a
Next semester?
computer science branch of IEEE that is going to be focused on quantum, and that's led by one of the PhD students in the computer science department. So.
Yes, actually that is the group we're talking about. Dr. Yuzili, Dr. Mailing Shayu Ahmed Hassan, myself, and Dr. Damin Zhu from physics. So 5 of us, we are meeting sometime this week to talk about, it was an initiative taken by Dr. Damin Zhu from physics and Yuzili from computer science to start, and also civil engineering also, faculty also wants to join in that discussion. So we'll be having most likely a first quantum computing course next year.
Next year.
So, if we summarize everything we have discussed in terms of memory classification, what we see? Memory, in terms of their functions, can be divided into 3 groups: read-write memory, non-volatile read-write memory, read-only memory. Read-write memory, all read-write memories can be random access type or non-random access type. Although this one and this one are also random access type, but we have restricted the term random access memory, RAM, only for random access read-write memory, because that, as I said, that class was introduced before these were invented. So under read-write memory, we say that one subclass is RAM, random access memory, and another subclass is non-random access memory. These are FIFO, LIFO, shift register, and CAM memory. Hardly used. We are not going to talk about any one of those. But frequently used memory types are RAM, flash, and read-only memory. So we will talk about this one, and this one. Design and operation in detail of these 3 types of memory. Before we introduce the design of these 3 types of memory, random access read-write memory, non-volatile read-write memory, and ROM, we want to introduce some basic definitions and terminologies regarding memory and some peripheral devices today. First one, we want to elaborate on memory timing. There are 3 timing parameters all of you must be aware of. One is called read access time, second one is called write access time, third one is called cycle time. Read access time. What is the most common application for memory? You read information out of the memory. So read access time is simply put, it is the time you need to correctly read an information out of the memory. It is called read access time. But for engineer, there has to be some reference time point to calculate that access time. Similarly, write access time. The second function we all perform in memory, we write new information into memory. The time it takes for your system to write a new binary bits into the memory is called write access time. Now, depending on the technology and the size and the nature of the memory, read access time and write access time can be different. Hardly they will be equal. So the memory cycle time is greater of these two. So when you as a designer, you have to design a memory with long enough cycle time so that you can accommodate read operation or write operation, whatever you want to do. On a single memory bit, you cannot do both read and write at the same time. In one cycle you may read, in the next cycle you may write a new data into it. So, but in each case, your clock cycle should be long enough to accommodate enough time to finish its reading or its writing. So the memory cycle time is the longer of these two. So these are the 3 times. So typically, as I said, as an engineer, we have to have some reference point to calculate this read access time and write access time and cycle time. Let's say a signal must be sent to your memory that a read operation is coming. So this is called read activation signal. A memory will receive a read activation signal to let the memory know that a microprocessor is going to read one of your bytes or bits. So memory will be powered up, activated, and be ready for read activation. And the read operation will start. After some time, that information will be properly copied from memory bit into the data bus for the CPU to read, right? So from the activation of the read signal to the availability of this shaded, let's say this is my bus, this is the data I'm looking for. When data is copied into the bus, so there is a time difference, right? Because we are going through some physical electrical circuits and devices, right? It cannot just deliver it instantaneously. It has to travel through transistors and wires. So that time is called read cycle time. On the other hand, write cycle time is, first we have to activate the write signal, deliver the data from the bus to the memory unit, and the memory unit should be able to properly copy it into its output node, right? So from the activation of the write signal to the final copying of the memory value into the output node of the memory cell, that time difference is called write cycle time. And the longer of these 2 times is your memory cycle time, because your cycle time should be long enough to accommodate whether you are trying to accomplish a read operation or write operation. Now, let us look at the memory architecture. This memory architecture discussion, what we will be presenting in the next few slides, will be common to any types of memory. We are talking about the overall memory architecture. Inside that memory architecture, individual memory bits or cells can be RAM, can be flash, or can be ROM, right? So we are talking about the general architecture of the memory first before looking at their individual design and operation. So, in typical memory, there is no memory less than 1 gigabytes or hundreds of megabytes right now, right? That means there will be millions of bytes, each byte consisting of 8 bits minimum. So now, if you have even a 1 megabyte bits, you cannot store entire 1 megabyte in one row. Then your memory will be several nanometer thin, 100 meter long, right? So you have to stack them in vertical and horizontal order. For very small memory size, each row can have one word. Now, how do you determine word size? Word size is determined by this kind of architecture. If your memory architecture is 16-bit, in one word, you can store 16 bits, meaning 2 bytes. If your memory architecture is 64-bit, in one row, one word, you can store maximum 8 bytes. 8 in one word is 8 bytes, right? So, in large memory, so there will be memory bits in multiple rows. Each row will contain one word, and the size of the word will be size of the memory architecture. So that is, so in that case, let's say you want to access, you can access only one word at a time because your bus can carry only one word at a time. So let's say you want to access this particular word. So then, since they are stacked into multiple row, multiple word, I have to have some signal line for each row, which is called selection line. Selection line, right? And that selection line must be controlled by a peripheral device. We'll talk about it later. But this one, it is called memory core. If the total, let's say if the total memory is m bits, m number of bits will be organized in multiple words, maybe n number of words, 0 to n minus 1, and each word will be containing certain number of cells, which will be equal to m divided by n, right? If the total number of bits you are storing is m, if the total number of rows or words you have is n, each word size will be m divided by n, right? But you have n number of words and you will have n number of select lines. The question is, at a time you can read only one at a time. So you have to have a mechanism to select that particular selection line and activate only that word and access only that word. Once you activate that line from these row signals, it is called row activation line. The data will be delivered to the bottom. Here, the buses will be connected. If it is a 16-bit bus, the word size will be 16. 16 vertical line will be running up and down, connected with every word. But that 16 line running vertically will get information only from that word which is activated. But now, how do I select the word I am going to activate? Your CPU will tell, here is the address I want to access in the memory. So each row will have a digital address. Each row will have a digital address like houses in your subdivision. So now I have to have an address decoder or row decoder. The digital CPU will send the signal. Row decoder will select the line that needs to be activated. So that particular word will be activated and the data will be delivered to this vertical line. How many lines? Will be dependent on 16, 32, 64, whatever your bus size. So the entire word will be delivered to your bus. So with the memory core, the first peripheral device we need is called address decoder or row decoder. In each row, there will be one word, and vertically there will be n number of words, and decoder will be have n number of selection line. At any time, it will only activate one selection line, providing access to only one word at a time, delivering only one word at a time to this vertical bit line, which is connected to the bus, memory bus. So the first peripheral device, first component of the memory architecture is the core itself. But with the progression of memory size, if your word size is, let's say, limited by 64 bit, if your memory becomes from 100 megabytes to 1 gigabytes to 2 gigabytes, that means vertically you have to now add more address, then it will become a very tall memory, get out of the chip, right? Because your chip size is limited by 2 to 3 centimeters. So how do I do? Then we don't have the luxury to put only one word per row, right? So what do we have to do? We have to subdivide the memory into smaller blocks. That means in each row, I have to put multiple words. So it is distributed vertically and horizontally. So now the question is, your memory bus is still 64 bit and it can read only one word at a time. But by row decoder or address decoder, now we are no longer calling it address decoder. Now we are calling it row decoder. The row decoder, let's say we activate this row, all the words in that row, 2, 3 or whatever number of words you preserve in that row, all of them will be activated. But your memory bit line can read only one word at a time. So I need a second decoder, address decoder called column decoder. So within that activated row, I need to read this one. So the column decoder will select either this column or this column. So combination of row decoder and address decoder, two address decoder is like a row, streets and avenues in Manhattan. You have to know at the intersection of which avenues and street, right? It's a perfect grid, right? It's called Manhattan grid. So address decoder, the row decoder and column decoder. So row decoder will activate this entire row and column decoder will select one word out of that row by activating one specific column. So I can store more in each row. I can have 3, 4, 5. So then I can, by arranging them horizontally and vertically word, I can now have a reasonable form factor, widthwise and lengthwise, right? But even further, so now memory core, still one core with multiple words per row, with multiple column, right? But it's, even with this one decoder at the row and one decoder at the column, with the progressive increase of size of the memory, the rows are becoming too long, the columns are becoming too long for the word line and the bit line to read them. So in the complex memory, in 1 terabyte memory, probably we have to put 1 million row, 1 million word per row, or maybe 10,000 word per row. Then it is becoming, the word line now is overloaded with too many words. The column line will be overloaded with too many words vertically. So the system will become extremely slow. So what we can do? We will talk about sense amplifier a little bit later. Now in modern complex memory, we divide them into multiple blocks. The core is divided into multiple blocks. 1, 2, 3, 4 blocks. Maybe if you have a 4 gigabytes memory, each block will be 1 gigabyte, and within each block there will be columns and rows, each row will carry many words, and each block will have many columns and rows, right? So then now I need third decoder. First decoder will select the block I want to access. Second decoder will activate a certain row in that block. Third decoder will select a particular column within that activated row. Thereby I can combination of 3 address decoder, column decoder, so row decoder, column decoder and block decoder together can pinpoint the exact address or word we want to access. But still I am limited by whatever 16-bit, 64-bit or 128-bit. But the memory now can be divided into small blocks like this periodic table. Let's say each one of them is a block of memory, so it can basically, I can have a fairly reasonable comparable rectangular shape, right? So now in terms of peripheral, so we have now memory cores divided into multiple blocks and 3 peripherals: address decoder or row decoder, column decoder and block decoder. However, so what is the advantage of breaking them into multiple small blocks? Each row line and each column line can be now shorter because we are dividing the core into smaller blocks. So the roads, streets and avenues will run shorter, so the signal traveling speed from one end to the other end of any row will be much shorter. If you implement the entire memory as one block, then when I'm activating this row, I'm unnecessarily activating hundreds and thousands of words in that row for no reason, because I'm accessing only one word. But if you divide them into smaller blocks, each time I'm activating a row, I'm activating only a very small subset of words in that row. All other blocks will remain turned off. So that will increase the memory access speed, memory read speed and write speed. Also, the biggest advantage we get, the second biggest advantage, first advantage is the speed of operation will increase because the row line and the column line will be shorter. Second biggest advantage is power saving. Your memory core consumes 75% of the power in your microprocessor. Once again, your memory core, roughly 70 to 75% of power will be consumed by your memory core if it is not controlled. So in a hierarchical multi-core memory design, what is the benefit? If I divide my 1 gigabyte memory into 4 blocks, at a time I am only activating 0.25%, 25% of the memory. 75% of the memory, 3 blocks, I don't need to turn on because I'm not accessing any data from that block, right? So speed and power savings, these are the 2 advantages why we divide memory into smaller blocks. But up to this point, what we found the memory core is the core where memory bits or cells will reside. It can be a single core or it can be divided into multiple core. And we need 3 types of address decoders if we divide it into multiple core: row decoder, column decoder, block decoder address. But there is a 4th peripheral device that is attached to any memory, irrespective of whether it's one core or multiple core. It's single row or multiple row. That is called sense amplifier or memory drivers. It is related to the statement I just made. The memory core, if you do not control, it will consume 75% of or more of your total power budget for the microprocessor. Why is that? Because memory is the most densely packed circuit component where millions and billions of transistors and wires, they are organized in rows and columns, and they are you are always accessing them for information, reading, writing, right? Storing, right? So that is always active no matter what you do, and that is very, very densely packed. So per unit area inside the memory core, you have highest amount of temperature generated. So the thermal stress and resulting power consumption and thermal stress will be highest where the memory core resides within the microprocessor chip. To minimize that, it is a standard practice in memory operation not to allow them to make a full voltage swing from 0 to VDD or VDD to 0. How can we do that? First of all, let's look at from electronic voltage point of view what we are doing when we are reading or writing a binary 1 or binary 0. When you are, let's say, writing a binary 1 into a memory cell, you are sending a high signal equivalent to VDD into that memory cell to raise the output from 0 to VDD. When you are reading or writing a 0 from a cell, you are lowering down, or you are sensing, you are seeing here whether this voltage is going up or down. If it goes down towards 0, you get the 0 voltage, then you make a decision that I am reading or writing a 0, right? So you reading and writing a 1 means you are raising the voltage to VDD. You are reading or writing a 0 means you are lowering the voltage to the ground. So in a regular operation, you have to wait for this battery or whatever is supplying that signal to make transition all the way from VDD to 0 or 0 to VDD for you to properly interpret or read or write whether it's a 0 or 1. But in memory application, in between the signal line and the memory cell, a set of amplifiers are appointed. Their job is just watch the signal for certain time from 0 to, let's say, 0.25 VDD. If it is continuously going up from 0 to 0.25 VDD, amplifier will interpret that a 1 is coming. So it will cut off the signal, it will amplify the signal quickly back to VDD. So your signal line will see an amplified VDD, so your memory doesn't need to make the transition all the way to VDD. Cells amplifier will amplify that. So your memory doesn't need to consume all the power it needed for making a transition from 0 to VDD. Rather, power will be from 0 to 0.25 VDD, then stop. Sense amplifier will take over. It will amplify the signal and deliver a full strength VDD to the outside. Yes.
Would that also make it more sensitive to noise then?
Yes, and that's why the memory cores must be well guarded. So all the noise control techniques are applied in and around memory circuit. So the memory circuit, when you design, every possible noise control, noise reduction techniques available in digital world must be applied to the memory core to protect it from noise disturbance. Of course, sense amplifier will consume some additional power, but when you are talking about millions and billions of bytes, not making full transition, because we know that power consumption is what? Proportional to CL VDD square. If you can reduce voltage swing instead of 0 to VDD to 0 to 0.25, right? 0.25 square is a very smaller value. Because of the quadratic dependence on power consumption and voltage, slightest reduction of voltage swing will give you huge savings in terms of power consumption. That will translate to significant drop in thermal stress. That's why, theoretically, without a sense amplifier, you can read and write memory any way you want. But you have to wait for memory cell to make full 0 to VDD or VDD to 0 transition. But the memory is placed in between memory cell and the signal line, If the sensor sees that memory cell is experiencing an upward transition, it will automatically interpret that a 1 is right coming. So it will amplify it, deliver a 1 to the outside one. If it sees that it is going down, it will amplify it, produce a 0, and deliver it to the outside one. So that is the fourth peripheral device, also known as memory drivers. So now in conclusion, along with memory core or cores, we need 4 peripherals to properly run and operate any memory system. Row decoder, column decoder, block decoder. These 3 are commonly known as address decoder. And then a set of sense amplifier or drivers attached to each bit line coming out of memory bus. And then, of course, you need control, because all the 3 sets of decoders, sense amplifiers, and memory core, they cannot operate randomly. Some additional circuitry must be there to control and synchronize their operation. So we have to have a control block. So we came down to 5 peripherals in any memory system. 3 decoders, sense amplifier or drivers, and 5th one is control circuitry. So 5 peripherals plus the core will make the memory system, plus of course the memory bus. Memory core and memory bus, these 2 are the main component, and everything else will be called peripherals. And memory bus, you as the designer, you have absolutely no control. You have to design the memory for whatever bus size or bandwidth given to you. Go ahead.
For larger memories like RAM, in your typical computer, I think you also have another decoder for doing chip select.
Well, depending on where you are using, how you are using, there can be many additional peripherals. Some of them will be optional purely for protection of the memory. Let's say we have to not only preserve the memory from noise, because the memory are allowed to operate at a reduced voltage swing. Instead of full 0 to VDD or VDD 0, they are designed to operate on a low voltage swing. So the transistors and all the circuits are scaled down to accommodate more memory cell in the small area. So they are not capable of handling too much power because they are designed for low voltage swing. So we have to protect the memory core from power surge or anything. So there has to be many additional protective peripheral on the motherboard around the chipset. But I'm talking about only the bare minimum required peripherals for the memory to operate. We're not talking about any protective device in this case. Yes, go ahead.
Can you move after that block?
Yeah.
So I just wanted to understand, these blocks are divided. So do these blocks have the same information, or do these blocks contain same information? Or
No, not same information. So let's say I have a 1 gigabyte memory I'm designing. I am dividing them into 4 cores. It's like I have too many files, so I need to distribute them into 4 different drawers, but each file is unique. Same thing, each word is carrying one unique word, one unique bytes or set of bytes, and within that bytes, individual bit combinations can be different, right? Because when memory size and information is exponentially growing, so we have to provide more spaces to store them. So we are dividing them into multiple core, within each core, hundreds of rows and hundreds of columns, right? So this is like, in general, the memory architecture. And then in the next class, we are going to talk about now deep inside memory core. As I said, we are not going to talk about memory bus. because that bus is determined by the system for which you are working for. Your operating system, Windows, and the system designer will predetermine that for you, whether it's a 128-bit architecture, a 256-bit architecture, or 64-bit architecture. But inside the memory core, you as the VLSI designer, your job is to design ROM, non-volatile read-write memory, and random access read-write memory, commonly known as RAM. Those serial memory people we are not going to discuss. And when we talk about RAM, popularly, we know there are two types of RAM we use. One is static RAM, one is dynamic RAM. So, that's all for today. We are not going to introduce any ROM design, but I request you to spend, like I repeated from lecture 2 and 3, spend some time on these initial slides up to slide number 10 to familiarize yourself with memory classifications and basic definitions. Because as you see, we have introduced like more than 12 terminologies and 6 different classifications, right? So you have to familiarize yourself. So next class, I will continue on memory lecture. End of the class, there will be a quiz on lecture 6 and 7. Due to technical difficulties, I am not able to recover as of now the recorded notes from lecture 8. Probably I will just go ahead and lecture to myself and record lecture 8 again and upload it.
But in Zoom class, only lecture 8 was informed or
Yes.
7?
No, only lecture. Yeah, last part of 7 and first part of 8. So, yeah. So the lecture 6 and 7, go through the slides. We will have a quiz on lecture 6 and 7 at the end of Thursday's class. Either I am getting old, my brain is not working.